Yeah. Good afternoon. I'm really nervous, so I'm sorry. Because today I'm really talking about two of my passions and my free time activity, and it would be like malware and logical programming. And because I love both of them so much, I try to put it together. So I'm starting giving a short introduction on logical programming and SMT solvers, and then I move to the practical applications that I have for in IT security. And then I will try to show how I help myself out doing static analysis using the SMT solvers. So that's just blah, blah, blah disclaimer. And for those that don't know me, I am a physicist. I'm now, since March this year, a computer scientist. But I have a physics background. I studied cosmology and astrophysics, so I'm new to the IT security, and I am a malware researcher now. So first of all, I would like to talk about SMT solvers, as I said, and SAT and SMT solvers, they are like as solvers for huge systems of equations. So the difference between both is really simple. The SMT solvers can take like arbitrary format, can be any kind of equations, and SAT solvers, they just can solve Boolean equations. And they need to be in the CNF format. So a lot of the real problems that we have like every day, analyzing malware, for example, can be represented like problems of solving this system of equations. So I heard a lot of people saying, like this year, that SAT and SMT and constraint programming, that's just another hype, and it's going to be like just for some months now. But I don't believe in that, because SAT is really old, and it's a fundamental principle in the computer science. And I believe that the reason that the interest is increasing right now is because the computers are getting really faster over the decades. And before, it was not possible. It was really inaccessible to solve problems using SAT and SMT solvers. And now we have like physical possibilities of doing it. So first of all, what are constraints? If you think about programming, you have like two different styles of building structures and elements in computer programs. The most used one is like the imperative program that everybody knows, just stating commands, like you are giving orders to a child and the computer will perform it. And then you have the funnier part, in my opinion, you have the declarative programming. So you are trying to express the logic of the computation for the computer without describing how it should really compute the result. So I really believe that he is right, because that's why you have computers for, to solve the problems that you don't want to solve by yourself. So if you want, if you need to really describe how the program is going to solve the problem for you, you're already solving it in a way. But if you have the problem and you know what do you want to have, why don't let the computer solve it for you? And of course, there's theoretical limitations on it, but I did a research and I really realized that circa 95% of all the constraint satisfaction problems that you have in finite domains, like in the industrial applications, not like the theoretical problems, they can also be written like a combinatorial problems. So you can also solve with programming. Of course, if you have like infinite or complex domains, you need to maybe assign some values and make like tainted or concolic execution, but it's still possible. So don't worry about the picture. I'm not trying to explain how SMT solvers work. And I'm not really talking about like predicate logic or something like that. I just want you to understand that SMT solvers can be seen like a black box. You have a problem, you have a goal, you make an equation of it, like a function, and you put inside this black box. And this black box will just say to you, is it feasible or not? It will deal with all the logical connections that you have with your problem and with your goal. And even better, every time that this black box thinks that their problem is feasible, the solution that you have is feasible for the problem that you have, it will also give you a solution. They are called instances, but that's just naming, it's not really important, but you have an instance of solutions, so multiple solutions, not just one. And maybe it's easier to understand the background of the black box if you understand who created this black box and why is it, what was the primary goal of having this kind of black boxes. The mathematicians were the first one trying to prove theorems, and nowadays you also have computer scientists working on hardware and software programming and verification. And automation was used from the mathematicians to make their lives a bit easier, making possible to state and prove like thousands of really, really tiny theorems, leading to the bigger goal that was like proving really difficult problems in the mathematics. And in the same way, you can make the large-scale verification of hardware and software accessible and reliable, because you can also like state really tiny theorems for your software. And writing like small formulas that imply the correctness of the program, you can make it scalable for bigger programs. What I mostly use in the IT security is the part of the symbolic execution. So the symbolic execution of a program will generate like a structure coverage of the code. So making like a control flow and making a constraint analysis of the multiple paths. That means that it's possible to determine like in every single branching, in every single line of code, the set of conditions that are necessary to really reach that goal. So every variable on your graph that it's created is, it will be represented as a symbolic value and not a concrete value. And each branch will have like a constraint solution set. And in this way, the symbolic execution, you use the constraint solver and allow someone to really find the path going from the entry point of the program to the end point that you think like, here is the malware code and I want to know what trigger inputs I need to reach the malware code. So, and how can I use it in the IT security? You can think about, like, as I said before, you have a problem and you have a goal that you want to reach. And in the IT security, you could think about a model, really simple, like, I want to say that my program is secure. So I could write a logical rule that if my program is secure, that means that nothing bad ever happens with my code. It's always working. And the SMT solvers, or if you use like Prolog or some constraint programming language, you use a technique that named backtracking. So it will just state, okay, so I will negate the first one, and that will mean that the second one cannot be reached. And so I would say, like, if something bad happens, that means that my program is not really secure. So the ways that they are using SMT solver already in the IT security, it's like for bug hunting, that's really common, that's really known. Almost all the CTF players are using it. And it would be like for fuzzing, that's like automated software testing, it's not really new. The only thing that for the IT security is really interesting is like, what do you want to fuzz? And an effective fuzzer would be one that is generating like not invalid inputs, but some kind of semi-invalid inputs, I would say. That would mean they are valid enough that they won't just break the parser and not even get to the real code, but they are invalid enough so you could find the parser flaws or something else like that. And for security, I would like fuzz maybe the code that it's in the HR website, receiving uploads of CVs from everywhere in the world, and not care much, even caring a little bit, to fuzz the code that it's just related to the configuration file of some sysadmin account. Another way of using SMT solvers that it's also known is like proof of concept. It's just like demonstrating some principle and blah, blah, blah. It's not so exciting. I really prefer the automated generation of exploits. That means you use the fuzz before, you find the vulnerabilities, you find the flaws in the parser, and then with symbolic execution, you have the set of all the values that are triggering this vulnerability. That means you can automate generate exploits. You don't need to think about it anymore because you find the failure and you have the inputs that are generating this failure. And then we are in the part that I most like, the malware analysis. And I use SMT solvers for all of this, but today I'm talking about the first one and the second one. So one thing that made me fall in love with malware was the duality of it. Because malware is technically and let's say for education, really interesting. And some techniques that you have in the malware are not really different than the things that are used, for example, in the software protection systems. In both cases, there is a program that it's doing something, and somebody puts something around it, like just to not allow people that are not allowed to see the program to get access to the code and actually understand what it's doing. So in one case, the objective is like to make the analysis of the program so difficult that the malware analysts have a talk time and figuring out what the malicious code is doing, and of course how to stop, neutralize, and write signatures or whatever. In the other case, the objective would be to make the analysis of the program so hard so that crackers cannot, or maybe have also a hard time figuring out what the key check program is doing, and they cannot neutralize this protection. So the important thing about that is that malware development is illegal in a lot of countries, but software protection is perfectly legal everywhere. So what leads to the main difference about obfuscating something is what are you obfuscating or what do you want to protect. It's nothing wrong with a program if you are protecting a program that it's just doing disk management or whatever, but it's really bad if instead of that your program is like encrypting everything and asking for a ransom. So now the interesting part, how it works. As I guess most of you know, the implementation of obfuscation code is really simple. It can be like just binary manipulation, like binary SHAR or something like that. But you can make it also complex, like using cryptography standards or whatever. In the world of the malware, normally it's useful to hide some words, that the strings that we call, because they give insights of the malware behavior. Like you could maybe share the where else or the registry keys or something that it's really easy to find. As you can see here, I wrote a really small script that it's just disassembling the code and counting how many code I have. And when I find a conditional jump, it will just test the branching. And it will test if a lot of code that you have in malware is like you have a jump that is never being taken. So you have like a whole tree of a graph here by IDA, if you know, and you don't need to look at it because it's just like garbage. And to automate this, I also wrote like a small script that it's just deleting the data that I don't need and analyzing the before and the end. That's an example of it, but it's not my real code because my real code is still running in a GPU and it's not finished for the presentation. But an easy way to deobfuscate this code and make the binary looks complex, like I said, is implementing a whiles or goto checks. And if you put like while true or something like that and write a code for when it's false, and you choose like in the compile no optimization, you still have the binary code for it. And then you have a lot of binary code that you don't need to analyze. And using the SMT solvers, it's possible to check all these basic blocks and look for ways to simplify the code if the constraint is not matched. So you know that this is never going to happen. You don't have the while false. So you are never taking this path, so you can just delete the whole tree of code. You can also use symbolic execution, but it takes way longer than just checking the constraints. Another way of obfuscate code is like using the char, as I said before, and probably that's the most commonly used method of obfuscation for malware because it's easy. And using SMT solvers and a bit of logic, like it was really just 4 lines of Prolog code, it's possible to create a script that will check for all the possible keys of the char function. It's like a char search or something like that. But as I said, there are 4 lines of code, so why you need a whole program for that if you can script it? And yeah, the code is still running also, so I could not even get a screenshot. But sometimes my malware writer go a step further, and they obfuscate the entire file. And a special program called like Packer. So using SMT solver is also possible to unpack this code without needing to run the code like with a debugger or something like that. Avoiding the cases where the actually malicious code is inside the self-implemented packer. So you can run in your machine and it's safe because you are not debugging. And that's just possible because the SMT solver will give you, like I said before, instances of possible unpacked code. And if you write like 2 more lines of code, you will get, like, you know, that's a PE file. So you can write a rule that say that your first binary will start with an MC, and then you know it's a PE file, and you don't need even to check for more instances because you just have 1 or 2. The limitation is like the Rice theorem, but I don't want to talk more theoretical stuff right now. It's just like simplify. You cannot write a program that will check another program. That's impossible. That's like Turing not complete. That's just an example of how symbolic execution works. And what I do is taking what is written in red, like the constraints, and use it to write like rules. And with that, I know exactly where I'm going to end because you have like, you can see errors, or 11 needs to be like 1,000 or 2,700 and whatever. So you can really find out what part of the code you need to look and which one you can just forget about. The problem with this is the precision of the graph that you are getting because of the performance of the analysis and everything. You need to configure the precision parameters to really have a good code. The problem with that is if you increase the precision of the control flow graph and have all the system calls and everything inside of it, you have way greater number of system calls clones among the graph nodes, and that's really complex, and you need a lot of power. So if you want to just have like a IDA graph or something like that, you should probably make a deal with yourself and think like, okay, I can understand the code like that, and maybe start a execution with input, start a not symbolic execution decode anymore. So in most of the cases, the static analysis, it will be a balance between what you want and what you need, and the availability of the resources that you have. Because this process it will be repeated for all the paths that you acquire. And afterwards, a set of these set formulas will be generated, and each of these formula that you have will represent one of the trigger conditions that you need for the discovery path. So you can imagine how many data you get. And to solve the whole equation system, it will take a lot of time if you are using something like Python, or not really fast. So it's probably, if you want something really, really precise, I would recommend to start programming in GPU style or something like that. So the conclusion is, if you want to use symbolic execution just for crackmes or CTFs, have fun. It's pretty cool, and I really like the technique, but you can also use it for work. Like, you can do it if you just take the time to learn how to program it. And as I said before, you can solve a lot of problems that before you needed to download some software for it, just scripting with 3 or 4 lines of code in Prolog. So it's useful to learn, and I think it's pretty awesome that you can let the computer solve the problem for you. And now you have the computer power to do it, so why not? So thank you.
Okay, thank you. Questions in the room? Yep. Is SAT solvers, SMT, etc. have like their
Sorry, I cannot understand.
Solvers usually formal logic usually has a sort of it's said there's certain limits with computing powers. Where did you run into these limits? Can you give us some examples?
Yeah, when I have a small binary, like I tried now at home just to have a demo, but it was not possible, as you see. I started like on Monday, and it's still running, and I'm using my gaming PC GPU, so you need a lot of power. But I guess it's not a problem anymore if you are in a company and you can just pay like some hours of Amazon, and then you have it. So I would say it's possible for companies or something like that to have this service, if you have people willing to do it. It's still resource expensive. Yeah.
Yes, because it doesn't scale linearly usually. It's like,
it's exponential. Yeah.
Exactly. So a lot of Amazon.
Yeah, that's the point. That's also one of the limitations that I'm working on, because you cannot generate the constraints on the beginning automatically. That you still need an analyst behind it saying for the computer which rules you need to start with. So you need the first maybe 3 or 4 rules to be written for an analyst that knows, like, here is the entry point and I want to go there. So, because if you want to symbolic execution the whole code, it's feasible, but it takes a lot of time and it can be expensive. So.
Thank you. So use all the Amazon.
It's the cheapest one.
So did you make any comparisons with some algorithms that are dedicated to do this? Because, for example, if you are solving or you are trying to find the code that is dead, you could do it in the way you said, by translating into some SMT instance and trying to solve it. But at the same time, you can write some specialized algorithm. So your approach is good because you've got like this like box that can do anything, but it is probably much slower than some specialized algorithm. So did you try to solve the same instance with some specialized algorithms and compare the time to your solution?
Yeah, I do it a lot. Almost all the times that I'm using my solution, I'm comparing with something that it already exists. And the thing is, yeah, it takes more time sometimes, but it's faster in the other cases. And I think my solution is a bit generalist because I don't need to know the algorithm. The computer will solve it for me. And if I think about all the people that I know, and I know a lot of good people in reverse engineering, even they cannot know every single algorithm in the world, but the computer can do it. So it's just relying on the computer power without spending time of experts, because they can do something else while the computer can figure it out which kind of algorithm it was used.
Okay. Any more questions? Okay. Well, thank you very much, Thaís.